Now we want to be able to find the maximums and minimums if we have functions of several variables. So remember, if we're graphing something with two variables, it looks like a 3D surface. And let's say we want to find the max or min. So in this case, it looks like we'd have kind of a peak here. And this would be my maximum. It's the highest value in that area. And this would be my minimum, still the lowest value in the area. And you can kind of see for either of these that you look at that on top of the surface it would kind of be flat. Or if you think about it, you kind of have a horizontal tangent. Or maybe you could lay a flat piece of paper across the top, or you kind of have a flat tangent plane. However you want to think about it, the tangent line is going to be straight there. And I can't really draw three-dimensionally very well, but you kind of have some flat tangent lines on top of it. And same thing with the minimum, it's going to kind of be these flat tangent lines. Okay. And here's the picture of the picture, and they're better than I am, and you can see that there's the x tangent line is flat there at the minimum, and the y tangent line would also be flat, or in other words, have a derivative of 0. So anytime you're going to have a maximum or a minimum, just like when we did this for one variable, the derivatives have to be 0. Okay, so again, if you're going to have a max or min, the derivatives have to be 0. So that means that we're going to have the derivative with respect to x will have to be 0, and the derivative with respect to y would have to be 0. Anytime you have a max or min, both derivatives have to be 0. So what we're going to do is we'll find any possible. Now notice this says possible because all the points I find aren't necessarily going to be max or mins. Okay, it's just possible max and mins. We'll find these possibles by setting both partial derivatives equal to 0, so both derivatives equal to 0, and we solve for x and y. Now our results will be in the form of some coordinate pair, and those are our critical points. And once again, they are possible max or mins. Not guaranteed to be either one, just possible. If we're going to have a max or min, it will be at these points. Now when we do this, we go through and we solve equations, and you're going to get equations like this sometimes, like 3x minus 4y equals 0, and 5y plus 7 equals 0, stuff like this. You're going to get what we call systems of equations. Okay? When you have two sets of equations and you're trying to solve them. If you don't remember how to do this from algebra, go onto Canvas. I have a specific section called Solving Systems of Equations. And basically you're going to be looking for substitution. There's other ways to solve systems of equations. This is usually the easiest one, or the ones that people remember the easiest. Okay. So again, to solve these systems of equations, you want to use substitution. And I have several videos of that on Canvas under the lesson page, or under the video page. So let's look at our example. So let's find points that might be maximums or minimums for this function, f of x equals x cubed plus y squared minus 27x minus 10y. So what we have to do, once again, is take both partial derivatives, set them equal to 0, and solve for x and y. So let's do the partial with respect to x first. So x cubed, that would be 3x squared, plus the derivative of y squared. Well, if we're worrying about x, we don't care about y, so it's just going to be 0. Minus the derivative of 27x would be 27. Minus 10y, once again, we don't care about y at the moment, so 0. Now we switch gears, and we do it with respect to y. So x cubed, we don't care about x at the moment, so that's a 0. Y squared, the derivative of that would be 2y. 27x, we don't care about that, so 0. And minus 10y, that would be minus 10. Now we're going to take these two equations and set them equal to 0. So I'm going to simplify as I do this. So 3x squared minus 27 equals 0. And 2y minus 10 equals 0. Now this is a very non-typical system of equations. Most of yours will be more complicated than this. Okay. I picked this one because it has a specific point I want to show you. So now we will solve for x and y. My first equation, notice, only has an x, so let's just go ahead and look at it and solve for x. So 3x squared minus 27 equals 0. 3x squared equals 9. X squared equals 3. Oh, sorry, I skipped ahead of stuff there in my mind. 3x squared equals 27. X squared equals 9. And x is going to equal plus or minus 3. Okay. Now let's look at my other equation. It only had a y, so let's use that equation to solve for y. So we get 2y equals 5, 10. Sorry, I keep skipping ahead. And y equals 5. Okay. So we know what x is, we know what y is. Now notice there's something interesting here. There are two x values. Okay. That means my critical points are 3, 5 and negative 3, 5. These are possible maximums or minimums. Now I say possible because in this section we don't actually learn how to tell if it's a maximum or a minimum or either. It's a lot harder to tell with these three-dimensional surfaces. It's a complicated process, so for now we're just sticking to these are the places where it might be a max or min. Okay, once you practice several of those problems, then we're going to figure out, okay, how do we tell if they're a max or min? And by that we can use the second derivative test, but it's very complicated. Okay, or maybe not complicated, but it takes a bit of work. So we found where our possible max or mins are. Now we want to see if they are max or mins. So this is the test, and this is just comes straight out of your book on page 365. So suppose that f of xy is a function, and AB is a point at which both of my partial derivatives are equal to 0. Or this is the critical points where I saw up above. So we're talking about the point 3, 5 or negative 3, 5. Then we have to calculate this function d. The way we calculate this is we take the second derivative with respect to x times the second partial derivative with respect to y minus the partial derivative where we took it with y and then x squared. Okay. So we have to find all these second partial derivatives. Then we plug in the point, our critical point, and if d is greater than 0 and the second with respect to x is greater than 0, then we have a minimum. Okay. If d is greater than 0 and the second partial with respect to x is less than 0, then we have a maximum. If d is less than 0, then it has neither a max or a minimum. Okay. This occurs when you have something that looks kind of like maybe a saddle. You can have a point that has horizontal tangents. It's not actually max or min. There is a picture of this in your textbook. Go look at that. And if d equals 0, then you can't actually draw a conclusion, and we don't really know anything about that point. So for example 2, we want to see if the critical points we found are really max or mins for this function, where we found the points 3, 5 and negative 3, 5 from up above. Now also from up above, I'm going to go through and write down our first partials so we can use them for the rest of this problem. Okay, so in our last example, we found the partial with respect to x, the partial with respect to y. Now let's find our second order partials. So let's do the one where we take the derivative with respect to x first. Okay, so we want to do it with respect to x first. Let's go to where we already took the derivative with respect to x and take it with respect to x again. So we're going to have 3 times 2x minus 0, or 6x. And let's take the partial with respect to y twice. Okay, so we come over to the y1, take the derivative with respect to y again, and we just get 2. And let's take the partial where we take the derivative with respect to y first and then the derivative with respect to x. Okay. So we said do it with y first because we work inside out, and then x. So when you look at that, do you see any x's? No. So the derivative with respect to x would be 0. Or similarly, you don't have to, but if you'd instead wanted to find the derivative with respect to x first and then the derivative with respect to y, you do x first. Do you see any y's in there? No, so the derivative with respect to y would be, again, 0. Remember how we said these two are almost always equal if we're talking about the kind of nice functions that we have in this class. So it doesn't actually matter which order you take those partial derivatives in. So we found all of our partial derivatives. Now let's calculate d. So d of xy is equal to the partial, second partial with respect to x times second partial with respect to y minus the mixed one squared. So let's find what d is at our critical point. So let's try the critical point 3, 5. So what was the second derivative with respect to x? It was 6x. So 6 times 3 times the second derivative with respect to y. That was 2, no matter what my y is. We don't care about y. All we care about is that it's just 2. Minus the second one squared. Okay, so my mixed one was just 0, so minus 0 squared. That's easy enough, so we get 1836. And d of negative 3, 5 is going to be, let's see, the 6x. So 6 times negative 3 times the derivative with respect to y twice. That was still just the 2. And my mix were 0. So we're going to get negative 36. So we found d. Now you have to go up to this table. This is probably a table you'll want on your notes because you probably don't want to memorize it. Okay. So we have 4 different conditions. We have conditions for if d is greater than 0, d less than 0, and d equals 0. So let's do our point 3, 5 first. So for 3, 5, d is 36. So for 3, 5, d is 36. So d is greater than 0. And in that case, it said we needed to see what the partial with respect to x is at 3, 5. So it's equal to 6x, or 6 times 3 is positive 18. So positive. Okay. So come back up and let's look at our cheat sheet. So if that second with respect to x is positive, it says we have a minimum at 3, 5. For negative 3, 5, d equals negative 36, so d is less than 0. So come back up to our chart. If d is less than 0, it has neither a max or a min. So it's just nothing.